Section 5.2, factoring trinomials. We're actually going to spend 2 sections factoring trinomials. And when we get into section 5.3, we'll see the difference in the 2 types. Right now, let's just start with some multiplication problems. Factoring is unmultiplying, so let's make sure we understand how multiplying works before we start factoring. Here's a pair of binomials, and if I multiply them together using FOIL, I have the first, the outside, the inside, and the last. Combine like terms. What we want to be able to do is take this trinomial as our problem, be asked to factor it, and give this pair of binomials as our answer. Let's get a few more up here on the board before we start figuring out how it is we're going to factor these trinomials. Let's FOIL this pair. The first, and watch your signs, the outside, the inside, negative times negative, plus 24 for the last. Combine like terms. Okay, let's do another one. FOIL this one out. The first, the outside, the inside, and the last. Watching our signs carefully. Combine like terms. And one more. And FOIL this out. The first, the outside, the inside, and the last. Combine like terms. And now let's stand back for a minute. And let's see if we can come up with any general approach to dealing with these types of trinomials when we're asked to factor. I notice they all start with x squared. All of my products, all 4 of my products, start with x squared. I notice they all end with 24, whether it's positive or negative. I see these 2 have 10s in the middle. 4 plus 6 is 10. I see these 2 have 2s in the middle. 6 minus 4 is 2. So I'm beginning to see some things here that might help me when I have one of these trinomials and I want to put it back in factored form. First of all, notice that in all cases, this 24, or negative 24 at the end, came from multiplying the 2 numbers in the problem, including their signs. Right here, 4 times negative 6, negative 24. Here's a negative 4 times a negative 6, positive 24. 4 times 6, positive 24. Notice that this coefficient on my middle term in all of my trinomials comes from adding those 2 numbers. I mean, look at it. We've got the outside right here. The outside was 6x, the inside is 4x. Combine like terms, we add them together. And so in all cases, the coefficient on that middle term came from adding my 2 numbers together. 4 plus 6 is 10. Minus 4 plus minus 6 is minus 10. Minus 4 plus 6 is 2. 4 plus minus 6 is negative 2. So as we start putting all this together, I realize that what I'm doing when I want to factor one of these trinomials is say that, well, if it factors, it'll factor as a pair of binomials. We're going to unfoil. If it factors, it will factor as a pair of binomials. And I'm looking for two numbers. I'm looking for two numbers because, see, when I'm factoring, I won't know this part. When I'm factoring, I won't have that. I'll be looking for that as my answer. So if the instructions are to factor this, well, what I know is that if it factors, it'll factor as a pair of binomials. For this trinomial to start off with an x squared, my two binomials have to start off with x's. That way, product of the first gives me that x squared. And then I'm looking for two numbers to fill in these two blanks. I'm looking for two numbers that when you multiply them together, they give me this numeric term, this 24. And when I add them together, they give me the coefficient on x, this 10. Can I think of any two numbers that multiply to give me 24, and at the same time, those same two numbers add up to give me 10? How about a positive 4 and a positive 6? And then, of course, I can check that by foiling, which we've already done. Another thing to think about is the signs. If the sign on my numeric term in my trinomial is positive, what does that say about the signs in my factored form? Well, if you multiply two numbers together and get a positive 24, what must be true about the two numbers? They were either both positive or both negative. So if this is positive, that means that the signs will be the same. If this is positive, that means the signs in my answer in my factored form will be the same, both positive or both negative. In fact, if these two numbers are of the same sign, and I know that their sum is positive, what's that tell you? My two numbers both had to be positive. If I have a product that's positive, which tells me that they must be of the same sign, in this case both negative, that's going to be shown by this negative on my coefficient on my middle term. If the two numbers multiply to give me a positive, I know they're the same sign. And if those same two numbers add up to give me a negative, then what same sign must they have had? They both have to be negative. Down here at the bottom, to get a negative 24, what had to be true? My two signs here had to be opposites. If this is negative, then I know I'm looking for two numbers of opposite sign. And in fact, if the sum of those two numbers is positive, then I know what? The larger of those two absolute values had to be positive. 6 is bigger than 4. It was positive. That's why we ended up with a positive 2x. Over here, 6 is bigger than 4. The 6 was negative. That's how we ended up with a negative 2x. So this will tell me that, in fact, the larger of those two numbers I'm looking for will be, in this case, positive. The larger of the two will be negative. Okay. So if I have a trinomial, I know that it will factor, if it factors, it will factor as a pair of binomials, each starting with x, because when I FOIL this back out, product of the first has to give me that x squared. So this has to be x times x. And we have also figured out that the two numbers that I have to multiply together to give me this number at the end. And my outside and my inside have to add up to give me this middle term. We know that if this sign is positive, then the two signs in my factored form will be the same. If this sign is positive, we know that the two signs will be the same. In fact, in this case, they will both be positive. And in fact, in this case, they will both be negative. If this term at the end is negative, then I know that in my factored form, my signs must have been opposites. If my middle term is positive, then the larger the two numbers I'm after must go with the plus sign. 6 is bigger than 4. The 6 has to go with the plus sign. And knowing that the last number is negative, these have to be opposite in sign, and this time, in fact, the larger has to be negative. Now that's a lot to take in, but it'll start to sink in as we work some problems and as you practice the homework. This is a good screen to come back to. This is a good thing to have in your notes so you can go back and look and see what we already know about our factored form just from looking at the form of the trinomial we start with. Now, in the textbook, she says the same thing here at the bottom of page 341. She describes it in words, saying that we're going to find two integers. We're factoring x squared plus bx plus c. Do you see that in the title of the blue box? Okay, so the c is like my 24 and her b is like my 10 here on the board. She says if we're factoring x squared plus bx plus c, then we're looking for two integers whose product is c and whose sum is b. All right, that's what we said. 4 and 6 are the two numbers I'm trying to find if I'm factoring. They have a product of 24 and a sum of 10. So far, so good. It says, number 1, the two integers must be positive if b and c are positive. Number 2, both integers must be negative if c is positive and b is negative. That's a lot of words to say what I have here at the top of the board. If c is positive, that is, if my numeric term here is positive, then they will be of the same sign. In fact, right here, this says they'll both be positive. In fact, right here, this says they'll both be negative. That's number 1 and number 2 in the blue box. Number 3 in the blue box, it says one integer must be positive and one must be negative if c is negative. That's my negative 24 here at the bottom. And I've already said that leads to opposite signs. And in fact, I went a little further and said, in fact, the larger of the two numbers I'm looking for will have the sign of that middle term. Let's make some sense of this by working some problems. Now, in all the problems in this section, the coefficient on x squared will be 1. Well, that's not entirely true. For the most part, it will be 1. If it's not 1, we're going to deal with it in a certain way that will be different in the next section. But what we're looking at is we are looking at trinomials of the form x squared plus bx plus c. In other words, the leading coefficient, the coefficient on this square term, is 1. In the next section, we're going to look at what happens when that's not 1. So these are the simpler trinomials to factor. Join me in the homework. Number 26. Number 26 says factor completely. I will never say factor completely. I will say factor. To factor is to factor completely. It says if a polynomial cannot be factored, write prime. We'll see what happens when we run up against one of those. Factor a squared plus 9a plus 20. This looks like one of these kinds of trinomials. The leading coefficient here on my square term is 1. So if this factors, it will factor as a pair of binomials, each starting with a. That's how I get my a squared back when I FOIL this back out. What does this tell me? Now, very careful, just answer the question I'm asking. What does this sign tell me? This sign does not tell me they're both positive. What does this sign tell me? This sign tells me that these two signs will be the same. And now, in fact, they will both be, right here, positive. Okay? This tells me that my signs will be the same. In fact, they will both be positive. And now I say I'm looking for two numbers to fill in these two blanks. I'm looking for two numbers. I'm looking for two numbers whose product is 20 and whose sum is 9. Can you think of any two numbers that when you multiply them it gives you 20 and when you add them up it gives you 9? How about 4 and 5? You could write 5 and 4. The order doesn't matter. There's my factored form. I can check this by FOILing it back out. Product of the first, a squared. The outside, plus 5a. The inside, plus 4a. Product of the last, plus 20. Combine like terms. Does this return the original trinomial? Yes, it does. And I'm going to encourage you to check every one of these by FOILing them back out. You don't realize how much factoring theory you will understand better just by performing these checks. I strongly encourage you to check each of these before you turn to the back of the book. Check them yourself by FOILing them back out, because that will reinforce this idea of how I'm finding these two numbers, 4 and 5, by looking for a product of and a sum of. Now let's say we got stuck on this one. And every once in a while, the numbers will be such that I get stuck. Okay, starting over. I want to factor this trinomial. Well, if it factors, it will factor as a pair of binomials, each starting with a. Right here, I know my signs are the same. In fact, they are both positive. And then I say I'm looking for two numbers whose product is 20, whose sum is 9. What two numbers will do that? Let's pretend that we're stuck and we can't think of two numbers that will do that. Well, there's a guaranteed method to find those two numbers. Let's look at this product of 20 and think of all the factor pairs that could possibly give me 20. Always start with the number and 1. 1 and the number itself. Well, 1 times 20 is 20, but do these add up to 9? No. Then we say, does 2 go into 20? Yes, 10 times. Well, 2 times 10 is 20, but does 2 plus 10 give me 9? Does 3 go into 20? 3 does not. Does 4 go into 20? Yes. 5 times. Does that add up to 9? Yes, it does. There are my two numbers. So I have this guaranteed method. We said back in chapter 1, being able to list all the factor pairs of a number was going to become very important to us. Well, it just has. Again, we saw a little bit of this in 5.1. But now it's even more critical here in 5.2 that you be able to list out the factor pairs of any number. I'm looking for two numbers whose product is 20, whose sum is 9. Once I find those two numbers, I've got my factors. And then I want you to check these by multiplying them back together. Let's try number 32. The instructions read factor. In other words, I want to unfoil this. I want to turn this back into a FOIL problem. a product of two binomials. Leading coefficient is 1. Good. That means that this method that we're working out here should work on this problem. If this trinomial factors, it will factor as a pair of binomials. This time, each starting with y. That's how I get y squared back when I FOIL this back together. What does this tell me? Answer only the question I'm asking. What does this sign tell me? That the two numbers I'm looking for will be what? Of the same sign. My signs will be the same. And this time, in fact, they will both be, right there, negative. So far, so good. Now, I'm looking for two numbers to fill in these blanks. I'm looking for two numbers whose product is 8 and whose sum is negative 6. Well, I've already determined that the two numbers are both going to be negative. So really all I need to ponder on is two numbers that multiply to give me 8 and they add up to 6. What multiplies to 8 and adds up to 6? How about 2 and 4? Now to add up to negative 6, of course, it's got to be a negative 2 and a negative 4. But I already had my negatives in place. I wasn't too worried about my signs. Those were already locked in. And this is the factored form. We can FOIL that back out to make sure it returns the original trinomial. And again, I want you doing that because you're going to get more out of this factoring process by checking it than you realize. You'll get faster at factoring by checking these. You can believe me or learn the hard way. Let's see what number 34 has for us. I need to factor this trinomial. If it factors, it will factor as a pair of binomials, each starting with t. Right here, I know my signs will be the same. In fact, they will both be positive. And I'm looking for two numbers. I'm looking for two numbers whose product is 12 and whose sum is 11. Now, what two numbers will do that? And if we get stuck, we can always go down the list. Is it 1 and 12 itself? That multiplies to give me 12, but does it add up to 11? No. Does 2 go into 12? Yes, 6 times. But do those add up to 11? No. Does 3 go into 12? Yes, 4 times. Does that add up to 11? No. Does 4 go into 12? Yes. However, I've already discovered that. That was the other factor in the pair with 3. I've just made a U-turn here at the bottom. I am out of factor pairs. These are the only factor pairs for 12. These are the only pairs of numbers that will multiply to give me 12 as far as integers go. As far as positive integers go, we know we're looking for both positive. These are the only pairs of numbers that will multiply to give me 12, and none of them add up to 11. What does that tell you? That there are no two numbers. There are no two positive integers whose product is 12, whose sum is 11, meaning this cannot be factored, meaning this trinomial is prime. Just like a prime number. If I wanted to factor 10, it'd be 2 times 5. If I wanted to factor 7 into prime factors, it'd be 7. Because 7's prime. It can't be broken apart any further. Well, this trinomial can't be broken down by unfoiling. So it's prime. I discovered that by listing these factor pairs of 12 in this case, and seeing that no factor pair of 12 will give me the sum that I'm looking for. Number 36. Factor this trinomial. If this trinomial factors, it factors as a pair of binomials, each starting with x. This tells me my signs will be the same. In fact, they will both be negative. I'm looking for two numbers. I'm looking for two numbers whose product is 36 and whose sum is negative 13. Now, I already know that both my numbers will be negative, so all I have to do is think, what multiplies to 36 and adds up to 13? I know they're both going to be negative. And I believe fairly quickly we come up with 4 and 9. And that would be our answer. Let's pretend that we can't discover the 4 and the 9 without going down my list. I mean, once you discover them, it's done. You write it, you got the answer. Check it. But let's pretend that we don't know it's 4 and 9. What would my list of factor pairs look like this time? I know that my numbers will be what? Same sign, both negative. So I start with 1 and the number itself, but this time it's a negative 1 and a negative 36. Do those add up to negative 13? No. Does 2 go into 36? Yes, 18 times. Does that add up to negative 13? No. Does 3 go into 36? Yes, 12 times. Does that add up to negative 13? No. Does 4 go into 36? Yes, 9 times. Does that add up to negative 13? Yes, it does. So my two numbers are negative 4 and negative 9. That's if I get stuck. If I don't get stuck and I can discover that 4 and that 9 without making that list, nothing wrong with that. But I want to be sure that you know how to use this guaranteed method of listing factor pairs just in case. Just in case you get stuck, or as we saw in the previous problem, if it turns out to be prime and you need to demonstrate to yourself, yes indeed, this is prime, I haven't missed anything. Number 40. If this trinomial factors, it will factor as a pair of binomials, each starting with D. This tells me what? My signs this time will be opposite. One's plus, one's minus. And in fact, the larger the two numbers I'm looking for goes with the minus. And now I'm looking for two numbers. I'm looking for two numbers whose product is negative 45. Signs belong to their terms. And whose sum is negative 4. Now, I already know they're opposite in sign. If I'm adding up two numbers opposite in sign, I'm really subtracting. So in my mind, I'm trying to come up with a couple numbers that when I multiply, I get 45. When I subtract them, I get 4. When I multiply, I get 45, and because they're opposite in sign, I'm thinking these two numbers need to subtract and give me a 4. Can you think of two numbers that will do that? How about 5 and 9? Now, which one goes where? For this middle term to come back out negative, when I FOIL this back out, the larger of the two numbers needs to go with the negative. So the 9 goes here, and the 5 goes there. If we were to pretend that we couldn't come up with those numbers, let's say, what would my list of factor pairs look like for this one? You always start with 1 and the number itself. We've already said these numbers will be opposite in sign, and the larger has to be negative. 1 times negative 45, that's negative 45. But do those add up to negative 4? No. Does 2 go into 45? No. Does 3 go into 45? Yes, 15 times. Does that add up to negative 4? No. Does 4 go into 45? No. Does 5 go into 45? Yes, 9 times. 5 plus negative 9, does that give me negative 4 for my sum? Yes, it does. And so there are the two numbers, a positive 5 and a negative 9. The more you practice this, the faster you get. The more you practice this, the easier it is to come up with those two numbers without making this list. And you better know your multiplication tables, up one side and down the other, like we've been saying from day one. Again, we can always check these, and I want you checking these. Let's FOIL this back out. Product of the first, d squared. The outside, minus 9d. The inside, plus 5d. Product of the last, 5 times negative 9, minus 45. Combine like terms. D squared, minus 4d, minus 45. That is the original trinomial that I was factoring. And understand what we're doing. Just like if I said, factor 15, and you do a little factor tree to get your 3 times 5, that's all we're doing here. We're factoring this trinomial into two things that multiply together to make it. Just like the 15 is 3 times 5, this trinomial is the product of those two binomials. Number 42. Factor. That's all my instructions will say. I will not say factor completely. I will simply say factor, and you will know to factor completely. If this factors, it will factor as a pair of binomials. We're unfoiling, right? Pair of binomials, each starting with m. Right here, my signs will be opposites. This negative tells me my signs have to be opposite. And this tells me the larger of the two numbers I'm looking for is going to be the positive number. The little guy will go with the negative this time. I'm looking for two numbers whose product is negative 30 and whose sum is positive 10. What two numbers will do that? And in my mind, I'm actually thinking, well, they're opposite in sign, so really I'm subtracting. What multiplies to 30 and subtracts to 10? What two numbers can you multiply and get 30 and at the same time subtract and you get 10? And if we get stuck, we can go down the list. Let's go down the list. Start with 1 and the number itself. And we said they're opposite in sign. The bigger one is positive, so the little guy's negative. Is it negative 1 and positive 30? They certainly multiply together to give me negative 30, but do they add up to 10? No. Does 2 go into 30? Yes, 15 times. Does that add up to positive 10? No. Does 3 go into 30? Yes, 10 times. Does that add up to 10? Nope. Does 4 go into 30? No. Does 5 go into 30? Yes, 6 times. Does that add up to positive 10? No. Does 6 go into 30? Yes, it does. But we've already discovered that. We've just made the U-turn at the bottom. We've run out of factor pairs. Telling me what? There are no two numbers. There are no two rational numbers whose product is negative 30, whose sum is positive 10. And so this can't be factored, and we write prime. I will accept the phrase cannot be factored or not factorable, but it is really preferred that you write prime. If you write no solution or undefined or any other thing that has nothing to do with factoring, I'm just going to count it wrong. With factoring, we don't have time to look for partial credit. Factoring is pretty much right or wrong. Rarely do I get partial credit for factoring because Factoring is a little tiny piece of some much bigger problems later on. We've got to get it right the first time, every time. Number 44. This guy looks a little strange compared to the ones we've been doing. Doesn't quite look like our trinomial that we've been working with. Well, that's because it's not in descending powers. These are easiest to deal with if we write them in descending powers. So let's go ahead and rearrange this to have the x squared up front, that linear term in the middle, my numeric term along with its sign here at the end. That looks like what we've been doing. Now factor. And if this factors, it will factor as a pair of binomials, each starting with x. Signs will be opposite, and the larger of the two numbers I'm after will be positive. I'm looking for two numbers. I'm looking for two numbers whose product is negative 39 and whose sum is 10. In my mind, I'm thinking, I already know they're opposite in sign, so really I'm subtracting. I need two numbers that multiply to 39, and when I subtract them, it gives me 10. This one shouldn't take too long to come up with. There are only two factor pairs. It's not 1 and 39. How about 3 and 13? 3 times 13 is 39, and 13 minus 3 is 10. In other words, opposite in sign and the larger one's positive. Opposite in sign, larger one's positive. I have two numbers that multiply to give me negative 39, and that when I add them up, they give me positive 10. The larger of those two numbers, the 3 or the 13, the larger of their absolute values, goes with the positive this time. And check these. Check these. You're going to learn more about factoring just checking these than you realize. The first, x squared. The outside, minus 3x. The inside, plus 13x. Don't those look familiar? The product of the last, minus 39. Combine like terms. And that works. Look at number 46. 46 is a little bit different critter, but not too bad. In number 46, we have an extra variable running around, but it's nothing to get excited about. Think about what kind of FOIL problem would have created this trinomial. I'd be looking for two binomials that what? Each start with an x, so that when I have product of the first, I get my x squared back. And what? Each end with some type of a term. Now these a's are going to have numbers on them, because I've got to get that 4 as well. It's going to start with a couple x's. It's going to end with a couple of a-type terms. Right here, my signs will be the same. Right here, in fact, they'll both be positive. And I'm looking for two numbers. I'm filling in these two blanks. I'm looking for two numbers whose product is that 4 and whose sum is 5. You know what two numbers I'm after, right? The two numbers I'm looking for are 1 and 4. 1 and 4 multiply to give me 4 and add up to 5. We don't see a coefficient of 1. Because the a is here, I don't write the 1. If the a had not been here, no need to write this down, but just consider for a minute. If I were working this problem, pair of binomials, each starting with c, signs are the same. In fact, they're both plus. Product of 4, sum of 5, it's got to be 1 and 4. I'd have to write the 1 this time, because there's nothing there to hold that term in place. But because this 1 would be a coefficient on a, I'm not going to see it. Let's check this one. The first, x squared. The outside, x times 4a is plus 4ax. The inside, a times x is plus ax. Product of the last, plus 4, and a times a squared. Combine like terms. X squared plus 4 of them plus 1 of them is 5 of them. And with the exception that I wrote ax and the original had xa, they're the same. Multiplication is commutative, so it doesn't matter what order the a and the x are in. This checks. All of the problems here from 45 to 55 have two variables in them. It just means they're going to start with one of the variables. It's going to end with terms of that other variable. You're still looking for two numbers. No big deal. Number 58. Now we're going to crank it up a little bit. Now we're going to talk about what we mean by factor completely. Again, all I'm going to say is factor. Now this one's a little different because it has a leading coefficient that's not 1. Are we sure this doesn't belong in the next section? Well, to factor means to factor completely. For example, if I were factoring the number 45, well, that is a factored form, but is it completely prime factored? We're not done. We've got this guy. He comes on down. But this one can be factored further. Now that everything is prime, I'm done. Look closely at this trinomial. Look at all three terms. Do you see that they contain a greatest common factor of 5? So what we're going to do, we're going to start by factoring out that greatest common factor. Factor out of 5, which will leave, and this is 5.1 right here. Factor out of 5. That will leave y squared plus y minus 6. Now what have we done so far? So far we've taken this trinomial, factored it into a monomial and another trinomial. There's nothing else can be done with this 5. He'll come on down, and we're going to see if this trinomial will factor further. That's what we mean by factor completely. And if it turns out that this trinomial is prime, we'll put a box around this because the original's not prime. I already got a 5 out of it. I already factored once, so I know it's not prime. But if this trinomial inside is prime, in other words, it can't be factored any further, I'd put a box around what I have. Let's see what happens. The 5 comes on down. Don't lose that greatest common factor. All right? That'd be like saying, when I did my 45, 45 is 3 times 3. You can't forget the lonely little guy that's already done. 3 times 3 is not 45, not without the 5 to go with it. So you can't lose that greatest common factor out front, or you've changed the value of the problem. And if this new trinomial will factor further, it'll factor as a pair of binomials, each starting with y. Signs will be opposite. And I'm looking for two numbers whose product is -6 and whose sum is, coefficient on y, +1. And what two numbers will do that? In my mind, since they're opposite, I'm thinking subtraction. I'm thinking what multiplies to give me 6 and at the same time subtracts to give me 1? How about a 3 and a 2? And what do I know? Right there. The larger of the two numbers goes with the plus. How about a 3 and a 2? Let's double check just that part really quickly. Product of the first, y squared. That works. The outside and the inside. The outside is minus 2y, the inside is plus 3y, and that totals plus 1y, or simply plus y. Product of the last, minus 6. Yep, that is how it factors. This is now factored completely. If you drop that 5, I'm going to have to count it wrong. Because what you would then have would not multiply back together by itself to give me this original trinomial that we were factoring. So don't forget that greatest common factor. Let's do another one. Number 66. Her instructions say factor completely. My instructions simply say factor. And you know that that means factor completely. First things first. Always, always, always check for a greatest common factor. Okay? That should be somewhere in your notes highlighted. Greatest common factor first. In any factoring problem, we will always, always, always check for a greatest common factor first. Among these three terms, look at the coefficients. They're all even. Greatest common factor among them is 2. Among my variables, I can factor out a k squared. This is just like section 5.1. If I pull 2k squared out of 12k to the 5th, it leaves 6k cubed minus 3k and plus 5. Is this factored completely? Admittedly, this is a tough one for us to answer at this point, but the truth of the matter is, you see this power of 3 on that k? There's nothing else I can do with this. This thing in parentheses is prime. And so, that's all it factors. I can factor out a greatest common factor, and then there's nothing else I can do with it. I mean, this isn't, it doesn't look like one of these. And we discovered there is nothing I can do with that. So that's factored completely. Number 72. Number 72 looks a little beastly, but he's not too bad once we start taking him apart. Little pieces, a little step at a time. First things first, always, always, always check for a greatest common factor. Is there a greatest common factor among these three terms? They all contain at least 7 x's. I can factor out x to the 7th. What does that leave behind? X squared plus 5xw minus 24. I took all the x's out of that one. Took all 7. 24w squared. Now, will this factor any further? This trinomial might. Bring down your greatest common factor. And if this will factor further, it will factor as a couple of binomials, each starting with x, each ending with some w term. The signs will be opposite. In fact, the larger the two numbers I'm looking for will be positive. I'm looking for two numbers to fill in these two blanks. I'm looking for two numbers whose product is negative 24 and whose sum is positive 5. Opposite signs, I'm thinking subtraction. What multiplies to give you 24 and subtracts to give you 5? 8 and 3. And we know the larger one has to go with the plus. And that's factored. If we get stuck, we can always go down our list. But this is now factored completely. And let's do one more. Let's have a go at number 78. Doesn't look like anything we've seen. Actually, it does. How many terms do you see? How many terms are there in this expression? Terms are separated by pluses and minuses unless those plus or minuses fall under parentheses. We see 3 terms separated here and here. Signs belong to their terms. Among these 3 terms, is there any greatest common factor? Is there any factor that all of these have in common? By the way, please don't make the mistake of thinking this is n minus 20. There is no n minus 20 in this problem. That n and that 20 can't see each other because you can't activate that subtraction until those products are dealt with. Okay? That's not what we're doing. We're not multiplying this out. Please don't multiply this out. That's just going to make it nearly impossible to get factored. Start by saying, how many terms do I have? Once I see how many terms I have, look for a greatest common factor. What if I'd given you this problem? How many terms do you see? Well, there are 3. Is there any common factor among these 3 terms? Well, how about that m? Well, let's factor out that m. What's that leave behind? Is this factored completely? I don't know. This trinomial might factor further. Now, with that in mind, do you see any common factors among the 3 terms in this original problem? How about this common binomial factor of x plus y? Same thing as if I had an m, except here I have a binomial. So what are you going to do? You're going to factor out that common binomial factor of x plus y, and what gets left behind? The n squared plus n minus 20. Are we done? I don't know. Maybe this trinomial will factor further. Don't lose your greatest common factor. He has to come on down to the next step. And if this trinomial in n factors further, it will factor as a pair of binomials, each starting with n. Signs will be opposite. The larger the 2 numbers I'm after will be positive. I'm looking for 2 numbers whose product is negative 20, whose sum is positive 1. So in my mind, I'm thinking subtraction. Opposite in sign, so I'm really subtracting. What multiplies to give me 20 and subtracts to give me 1? How about 4 and 5? The larger the 2 numbers goes with the plus. N plus 5, n minus 4. And that's factored completely. I would encourage you, in addition to this video, you seek out other videos on factoring trinomials whose leading coefficient is 1. Whose leading coefficient is 1. Other videos on YouTube about factoring trinomials whose leading coefficient is 1. Someone else might explain it in a way that snaps it into place in your head better than the way I've described it. Nonetheless, we need lots of practice. Lots of practice. And so You'll start with the homework problems. If you need more, holler at me for the even answers. If you need more, there are tons of resources on the internet. And you can find as many problems that you want to work. Right now, you're looking at trinomials whose leading coefficient is 1. Factoring trinomials whose leading coefficient is 1. Off you go.